G'day folks, it's me again. Well, for today's quick little video we're going to be looking at another big lamp. And here she is. It's another nice big BT56 outer envelope. Obviously it's a General Electric multi-vapor MVR 1500, designed for horizontal or base down burning. Kicks out 161,000 lumens with a core temperature of 3600 Kelvin. Colour rendering is about 65%. It's made in the USA. But this time it has an E39 cap, which is quite rare to find in the UK. And yeah, it's a nice big 1500 watt lamp. You might think it looks exactly the same as that 1000 watt General Electric lamp we've seen in the previous video, and you'd be correct, because it basically is. That stems from the good old days of the mercury vapor. They used to run 1000 watt lamps in sports stadiums, and they used to overdrive them to get a bit of extra output. Obviously that would reduce the service life, but in a stadium where that's not really a big issue, that was an acceptable trade-off. The same thing applies here, but the halide mixture inside has been tuned to operate at 1500 watts, but obviously it does actually have a really short life of only 3000 hours. So let's fire it up. But the thing is though, the control gear for this is, well, good luck trying to find that in the UK. I imagine even in America it's pretty rare, but I have got a way to get around that. Obviously the arc voltage is 268 volts, so it's a high voltage lamp, and the arc current is 6.2 amps. I should be able to sort something out. Let's have a look. In a previous video I cobbled together this gearbox. It has two 1000 watt ballasts. Each one is designed to run a single 1000 watt high voltage metal halide lamp on ordinary 240 volt mains, but I can run them together in parallel to run a single 2 kilowatt lamp. Anyway, what's inside each ballast is basically just a step up transformer and then a normal high voltage choke. Because the chokes are not auto transformers, you can run them in parallel and they work quite well that way. Obviously it's not ideal, but it works. So what I'm going to do in this case is I'm going to use a variac to lower the input voltage to get the desired lamp current. Here we can see the output from the ballast. There's 240 volts going in, and the open circuit voltage coming out is 430 volts. Before we fire it up, we just have to take a few precautions. Because this lamp is designed to run on some sort of constant wattage auto transformer, the maximum run current for the lamp during the run up is 9 amps. Obviously we're using chokes, so the run up current is going to be a hell of a lot higher. And that delicate little flywire you can see going to the top of the lamp, that will not like it, and it'll probably glow really red hot, and it might melt if we're not careful. So what I'm going to do is I'm going to fire the lamp up on a single ballast, and then when the arc voltage starts to rise, I'll use the variac to lower the input voltage, and then I'll switch on the second ballast, and then obviously further reduce the input voltage until we get to the desired lamp current, which in this case is 6.2 amps. So let's fire it up. Power in 3, 2, 1, 0. 7 amps, about 30 volts. This is only a single ballast. Pulling 7.35 amps, that's well under the limit of 9. Arc voltage is currently at 27 volts. And that will rise. Obviously you can see the low pressure mercury discharge there. When the lamp runs up, you'll see that start to decrease in thickness, and then you should see the metal halide start to vaporize. Let's just tone down the variable ND a bit. You might see some start to vaporize. That looks good. Lamp voltage is starting to rise. We're at 45 volts, 50 volts. Lamp current 7 amps. 60 volts. Let's try more ND. 100 volts, 110, 115, 130, 135, 140, 160, 5.6 amps, 180. Right then, we're getting up to 200 volts, so I'm going to full ND now. Oh. What I'm going to do now is I'm going to reduce the input voltage. Switch in the second ballast now. Wow, that's bright. Oh, jeez. This is a obviously a new lamp, and the arc is unstable. Oh yeah, that's bright. Lamp current 6.2 amps on the dot. Oh yeah, that's bright. To try and get a better view, I've turned the camera on its side. The top of the lamp is on the right and the bottom is on the left. Now you can see the arc stream is very unstable. It's doing its little dance routine. I am operating at the correct arc current of 6.2 amps, but obviously this is a brand new lamp, so it needs a few hours or a few tens of hours to stabilise. What it is the metal halides probably hasn't diffused around. There's probably not yet a cold spot, so the discharge is operating outside of its parameters. It is a really nice light. It's a it is a really nice colour, to be honest, and it's mega bright and it's kicking out a lot of heat. It's a good heater if nothing else. Yeah, I'll try and see if we can get a close-up of that top electrode. It doesn't have any thermal insulation around it because obviously this is designed to run base down mainly, so the top doesn't need it, whereas the bottom does. Let's do that now then. Here's a view of the top electrode. Not the sharpest view because we're looking through both the curved outer envelope and also the thick quartz arc tube, so there is a bit of diffraction going on, but you can see the electrode there. Do you think that's warm? Pan down a bit, go to the bottom. Will it refocus automatically, or will I have to do it by hand? There's the arc stream dance. I showed this on a video a while ago, but this is obviously the full lamp. Yeah. Anyway, I hope you found that interesting. Thanks for watching. Bye bye. If you're still here, thank you very much for watching. Right then, I'm going to kill the power. 3, 2, 1.